Okay, so our next vignette centers on trying to examine in some detail one of these gene regulatory networks that we just talked about in the previous vignette, which was an introduction to gene regulatory networks. And so the first one that I want to think about and that I quite like on many levels is the dynamics of autoactivation. This is a lot of fun, I think, so I hope you'll agree. And I don't know. I guess I say that in all seriousness, really. I mean, maybe it's not a very serious point of view, but we're lucky to be able to think hard about things and to take enjoyment from it. And I feel very fortunate to be part of a profession of which there are not that many, I don't think, where people get paid to sit around and do something which they would just do for fun anyway. And so anyway, okay, sorry, that was a little bit of a non sequitur, but so we're going to talk about autoactivation. And as I already introduced, autoactivation refers to the idea that I have a regulatory network where the gene product of the gene of interest is its own activator. So it basically forms this loop that you see here. And what we're going to do is we are going to use the statistical mechanics protocol in order to write down the states and weights, and then I'm going to write a production equation. In other words, I'm gonna ask the question, or I'm gonna try to assert that the number of activators at time t plus delta t is equal to the number of activators at time t, and then minus those that decay during the time interval delta t. So that's this term. And then I'm going to say times sum over the states, which in this case is 4. There's 4 states. And then I'll have r sub I and then p sub I, where this is the probability of the ith state. So what am I talking about? Well, what I'm talking about is shown up here in the diagram in the right-hand column. So I've added a new category, which is rate. And what I'm saying is that maybe the way I always like to think about this is either for you writing your thesis or for me writing a book or something, that I have an intrinsic typing rate, as do you. And maybe when I was a kid and I was in junior high, we had a class that was typing. And I don't know, I'm being a little bit obnoxious, but in many ways I feel like in junior high, it's a 3-year endeavor. I did that in San Diego, California. It was just an intellectual vacuum. And I remember actually thinking that typing class was pretty useful, and I think I got up to 60 words per minute. And we would sit in this room, and we all had typewriters, and we'd face the front, and the teacher would put up a thing for us to type, and we'd type, and you basically type and hit the return bar, and you could actually go reasonably fast. And my point is this, that you're typing your thesis, or I'm typing my book. I type at some intrinsic rate, let's call it 30 words per minute, and then I have to multiply by the probability that I'm actually engaged in the act of typing. So, like in this case, maybe I imagine that I'm typing when I'm in my office by myself, and that's my highest rate. And then there's a probability of being in my office. Then, even though this isn't actually true, but let's say that I worked in Starbucks and I tried to type on a book there, or you tried to type on a thesis, and your typing rate would not be the same. So then you'd take the rate when you're in Starbucks times the probability of being in Starbucks. And so basically this equation that I've written down here, or at least this part of this equation, is basically acknowledging that each one of these states has a different intrinsic rate at which transcripts are made. And the key point I want you to take away is that there's some basal rate of production, and then there is a second rate of production when I'm in the singly occupied activator state, and then there's a highest rate of production when we're in the doubly occupied activator state. So that's the essence of things. Now, let me also comment on the weights. This is going to look a little bit different than what we did before, but if you go back to the cooperativity vignette, you'll see that at some point, because I chose my zero of energy in a certain way, and I chose my multiplicities to be normalized in a certain way, that allowed us to write our statistical weights as 1, and then we had, an A over the number of binding sites times an exponential of an energy. And I'm just pointing out that can be equivalently written as A divided by some KD. This is the cooperativity parameter. So I'm saying in the doubly occupied state, there's a cooperativity. And so those are basically our states and their respective weights. And so if I do my usual thing, which is to bring my A of t to the left side and divide by delta t, what I'm going to be left with is dA by dt is equal to minus gamma A, and then plus R0 times 1 over z plus 2 times R1 times A over KD over z, and then plus R2 A over KD squared omega over z, where z is defined as 1 plus 2 A over KD plus omega A over KD quantity squared. It's just a simplified way for me to write the denominator without having to do all sorts of long expressions. It's nothing more than a labor saving point. Just remember, the probability of a given state, if I want the probability of this state, what do? I take its statistical weight, which is 1, and then I divide by the sum over all statistical weights, which is all of these. And that's exactly what I have here. The probability of this state is 1 over z, where this is how z is defined. So that's our equation for the dynamics of production and degradation of A. This will tell us the time evolution of A given some initial conditions. Now, this is a moment for us to remind ourselves about cooperativity and the Hill function. So I'm going to find it easier to think about the Hill approximation, and so we just talked about the various states of occupancy. So here's the empty state, this is the singly occupied state, and the doubly occupied state. So that's what I mean when I say P0, P1, and P2. And these three graphs show you the probability of empty state, doubly occupied state, singly occupied state. So I have three different states, and I'm looking at their relative probabilities. And once the cooperativity gets tuned up, as I said in the vignette about cooperativity, that middle state gets suppressed. It's as though the singly occupied state is really not part of the story, and that means that we can effectively pretend that the singly occupied states are not part of the problem. If I do that, then I'm going to replace the original states and weights by this modified, trimmed down, coarse-grained, simplified, abstracted, whatever you want to call it, version in which now I can write my differential equation in the form dA by dt is minus gamma A, and then plus R0 over 1 plus A over KD, quantity squared, plus R2 times A over KD squared over 1 plus A over KD squared. So that's my simplified version of the dynamics of the autoactivation switch. Now, you might be asking yourselves, why would you have chosen to write down this cooperative interaction? And I'm not going to go into it in too much detail, but I do want to alert you to the fact that had I not chosen a cooperative interaction, this thing would not behave as a switch. And I'll try to indicate that to you in a few minutes. So this is, just to recap, what we've done is we've basically used our states and weights. We've worked out an equation of the dynamics of protein production. There's a degradation term, and then there's these production terms, and the production terms are of the form R0 times P0, so that's what this one is. And then this one is R2 times P2, where this is the probability of the unoccupied by activator state. And this one is the probability of the doubly occupied state. So that's what's going on. Now, we're gonna have a great time here reminding ourselves of phase portraits, and this is something we did earlier in the context of just simple mRNA production. But this is much richer, this case. So let's stare at this. So what am I plotting? So this red line, let me label it in red. This red line is gamma A. So that's the degradation term. The green guy, which I will label in green, the green guy is R0 over 1 plus A over KD squared plus R2 A over KD squared over 1 plus A over KD squared. Let's look at the limits of this thing. When A goes to 0, this thing is R0. Okay, check it out. If you look at this whole beast and you set A equal to 0, all that's going to be left is R0. Now, in the opposite limit, when A is huge, this thing is going to saturate at R2. So let me write that up here. So this saturates at R2 up here. So, and it's sigmoidal. It's sigmoidal means that it has a change of curvature, as you can see here. So when I plot, I draw the production term, you see it's got this nice, interesting behavior. And when red is above green, for example here, when red is above green, that means degradation outpaces production, and that means that the amount of A is going to decrease. When green is above red, for example here, then that means that production outpaces degradation, and we're going to move to the right. dA by dt is greater than 0, and so the amount of A is going to increase in the next time interval. This is very beautiful because without even solving the problem, what we've figured out is that this thing has three steady states, 3 fixed points is the lingo. And we see, in fact, that 2 of those fixed points are stable, and 1 of the fixed points is unstable. What do I mean by that? When I say unstable, it means that if I perturb it slightly, it will fall out of that stable point and go to another. So you can see that by we actually here write these fixed points as filled circles because they're the stable ones. And this one is unstable because it is the point where the arrows point away from it. The length of the arrows is telling you about the magnitude of the drive. It's telling you about the magnitude of dA by dt in the next time instant. So this system has 3 fixed points. Now let's, and you'll have a chance to do this as a homework, but let's anticipate what will happen if you try to solve this problem for various initial concentrations of A. So if I start out with A equals 0, because of the R0 term, it's going to start to increase, and it will reach the first low value fixed point. If I start at very high values of A, it's going to come down to the upper fixed point. That corresponds to, starting out above, with a concentration over here, above the second fixed point. The third fixed point. So we will flow in to that fixed point. And if I start in the middle, well, depending on whether I'm above or below this unstable fixed point, I'll either go down to the low or go up to the high. And what I want you to take away from this is that I'm going to say that this circuit behaves as a switch. And the reason I say that is because it is either high or low. You can see that I'm turning the switch for the light in this room on and off, and that's effectively what this thing does, is it either goes to high or low concentrations. So that's our rate equation treatment of the simple autoactivation switch, and we actually had an opportunity to use a really interesting methodology. So first of all, we took advantage of our states and weights, which I told you I needed to think about binding and cooperativity before I could do some of these other rich examples of dynamics. So we exploited that. But we also did this very nice thing of writing down the phase portrait, basically. We looked at what the rate would be as a function of the number of activators. By the way, that reminds me, note, in this graph, the x-axis is time. And in this graph, the x-axis is concentration. Just do not be confused. These are different plots. This one is plotting rates as a function of concentration. This one's plotting number of molecules of A as a function of time. So at any rate, we were able to really push one of these dynamical systems, the sort of simplest one, all the way to the finish line, exploiting the quite cool nonlinearity of the binding functions having to do with cooperativity. So that's what I have on this one.